Okay, good morning, everybody. So I have the honor to preside this jury for the PhD of Saeed Bidi. So I will present the members of the jury, starting with the reviewers. So the first reviewer is Klaus-Dieter Hohl, is a professor at the University of Magdeburg in Germany, if I'm not wrong. The second reviewer is Apchi Shauki, is a researcher at IFPEN in Rueil-Malmaison. And then we have Marika Pelanti, who is a professor at ENSTA in Paris, or Palaiseau. Then myself, I'm Stéphane Popinet. I'm a directeur de recherche CNRS at Institut d'Alembert. And then your supervisors, so Manolis Kaveses, a professor at University of London, and then Stéphane Zaleski, who is a professor here at Institut d'Alembert in Paris. So you will have 45 minutes to present, sure. And then we will ask questions. So you can start whenever you're ready.
Sure. Thank you so much for this introduction. A very brief introduction of myself. I am Saeed Bidi, and I started this UCOM project at City University and Sorbonne University in 2019. And without wasting any time, let's move to the first slide, which is about the publication. So today, I'm going to be very brief about the mathematics, more focusing on the physics side and showing the main findings. But for the mathematical part and equations, we can always go to this list of publications. The first one is a kind of surprising thing. It got accepted just last week, which was a kind of gift before my viva. Let's move to the bubbles. The bubbles are very mysterious. And why do I say that? Because they can be fun. They can be destructive. They can have some applications for cleaning, for example. But another modern application of bubbles is for therapeutic purposes. So we can use bubbles for drug delivery. We can use high-intensity focused ultrasound in order to, to kill the cancer cells, for example. But one of the main applications of bubbly flows is in lithotripsy. So when we have the lithotripsy to break the kidney stone, we have cavitation here. And this is the main aim of my PhD. So if I manage to explain this well, then most of the things is solved. So this is the bubble. And we are seeing now the temperature of the bubble interior, which is the main aim of my PhD. We would like to use some advanced models, thermodynamic closures, in order to model this temperature accurately. And the second goal, which is again relevant to thermodynamics, is about modeling the temperature outside the bubble. So we are more curious now about the vicinity of the bubble, the temperature of the liquid in the vicinity of the bubble, and also the liquid temperature along this wall. There is a rigid wall here, so we are interested in seeing how the liquid temperature along this wall is evolving. So these are the two main purposes of the presentation today. And in order to get there, I will start after this introduction, talking about the modeling thermodynamics of the gas, and then we will move forward and we will talk about the liquid thermodynamics, why we pick some equations of a state for liquid, and following that, methodology. I picked two methodologies here. I will describe it later. So this is a very simple presentation of a bubble collapse, which is a spherical. So we have no external asymmetric forces. So the bubble is collapsing because the pressure in the vicinity of the bubble in the liquid is higher. So the bubble starts collapsing spherically. So this is the simplest case of bubble collapse. And here's the schematic of the problem that we are going to deal with. So we have a bubble, and it has a temperature and pressure inside, which is again lower than the one from water. And as it collapses, the pressure inside the bubble, it goes high, and this is where the problem starts. So the temperature goes to crazy value, like 5,000 to 15,000 reported. And as a result, we have thermal dissociation. We have, the chemical reactions and free radicals and everything. So the first aim here is to model this temperature and the gas thermodynamics here inside the bubble properly using advanced equations of a state. And in order to do that, the first option is to use ideal gas equation of a state. But the problem with the ideal gas equation of a state is that it doesn't include the intermolecular forces. And this is problematic because when we are at high pressures, we obviously have the intermolecular forces, or when we are at low temperatures, again, the intermolecular forces become dominant because the kinetic of the gas, the kinetic energy is less. So as a result, the dominant forces is their intermolecular, and we would like to have some thermodynamic model so that we can model them precisely. So we have a couple of options here. The first one is to use the cubic equations of a state, which I picked two of them, is the Peng-Robinson and an improved version of the Peng-Robinson, which we refer as RKPR. And the second one is, the second, let's say, alternative is to use the Helmholtz energy equation, which is based on experiments. So these are the general form of the equation of a state, the cubic ones. I'm not going into the details, but just it's enough to distinguish the cubic equations of a state from the ideal gas, because we have these two parameters here which they account for the intermolecular forces. And let's see what we have for the main thermodynamic variables that are from these cubic equations of a state. Again, I'm not going into the details. This is just to know that this is a bit complex to implement, to couple it with the CFT solver. And this is for the energy, the Helmholtz energy model, which again we have these two parts. They compromise they kind of compose this compressibility, and there is an ideal part and residual part. And again, there are some main thermodynamic variables associated with the Helmholtz energy model. And here is the best benchmark test that we could kind of use as a kind of analogy to the problem of bubble collapse. So we start compressing the bubble from atmospheric condition and in an isentropic way. And we could see that there is an overprediction of temperature when we use ideal gas. So as you can see here, it's like there is like 40% difference. We call it overprediction of the temperature prediction using the ideal gas. And the question for now is that how this overprediction can affect the bubble dynamics or the bubble thermodynamics, which I will be presenting in the next few slides. So in order to implement the tables, in order to implement the equations of a state, we try to make this structured table because, as I show, the equations of a state are very complex. So in order to couple the CFT solver with all of those equations of a state, it's probably easier to use a structured table and then to read all the thermodynamic variables from the table and to basically do some interpolation instead of using the parametric forms. And while I was doing the gas thermodynamic studies, I found that the problem of overprediction of temperature exists even for liquid. So what should we do? I said, okay, the first choice is a Stiffened gas, which is commonly used in the literature. And we can see here, the problem with the Stiffened gas, however, is that the specific heat ratio is usually set to 4.4 to represent the compressibility well. But for thermodynamics, this is not valid, obviously, and it cannot really give us a good approximation for the temperature because in reality, we have almost a specific heat ratio of 1. And another thing is that Stiffened gas doesn't include the repulsive forces. So I went for the alternative options. This is a thermodynamic proof that for what I was explaining. So we see here again, similar to the compression test that I just presented for the gas. We did the same for water as well, and we could see again a kind of a prediction here, which is coming mainly from not physical specific heat ratio, as well as ignoring the repulsive forces, the intermolecular ones. So I went through some more advanced liquid thermodynamics, and the first option was to use obviously the experimental data. But the problem with the experimental data is that they cannot cover the valid range for our problems that we wanted to consider for bubble collapse. So I went to the Tate equation of a state, which you can see the original form of the Tate equation of a state here, but the problem with Tate is that the density variation is not it's not a function of temperature. So the problem is that as we increase the temperature, we would like to see some changes in density so that we can have some, high accuracy solution in the end. And as a result, together with colleagues and also PhDs in particular, we developed this modified Tate equation of a state. So essentially, we are using two functions here, which describe the variation also with temperature. But the problem with the modified Tate was that it also had a limited range of validity. So I went to the other alternatives which are based on the Stiffened gas. So the first option is the Noble-level Stiffened gas, which is being very used during the last few years, which includes also the repulsive forces as we want. And there is another version of the Noble-level Stiffened gas, which is called the modified version. And the good thing about that is that it corrects the density. So it's a kind of improved version of this Noble-level Stiffened gas, but in terms of the equation, is the same. And by the way, I took this simulation here because I just wanted to show that based on my experience, the Noble-level Stiffened gas has some inaccuracy compared to the MNASG. So we picked this MNASG for the liquid thermodynamic solution, and this is how it can affect the results. So here is a very simple shock tube test. So we have this Stiffened gas here, which you can see a very noticeable over-prediction of temperature, whereas we don't see this. I mean, here for the reference, we can say that this IAPWS, which is based on the experimental data, this is the most reliable source that we have. So compared to this blue line, we can see that the MNASG has a more or less good accuracy. So among the options that we had, we went for this one. This is the section for methodology. So initially, I started with the 6-equation model. And then I also implemented this Kapila model, the 5-equation model, and I'm going to describe them, though not very completely, but if you have questions, I can obviously answer. So this is the structure of the 6-equation model. We have the volume fraction equation, also the equations for momentum, densities, and for specific internal energies for each phase. And in order to make sure that the total energy is also conserved, we also have this 7th equations, because the first thing intuitively come to mind is that we call this 6th equation, whereas we have the 7th equation as well. But the purpose of this equation is just to ensure that the energy is conserved. The main novelty, the numerical novelty that I had in my thesis in terms of just a numeric, is that the relaxation step, let me explain this to you in a bit more depth. We have two different pressures initially. As you can see, P1 and P2 for two components are not the same. So we assume that the phases or the components are initially in mechanical disequilibrium. But through a step called a relaxation step, which you can see the associated terms on the right-hand side, we try to equalize these two pressures so that we can reach the mechanical equilibrium between the two components. And in almost all of the studies that I could find with this 6-equation model, I could see that this relaxation step and reinitialization step were using ideal gas and a Stiffened gas. And in that case, we don't have any problem because there is an analytical solution for the relaxation step. But what I did was to make a generalized solution for the relaxation and reinitialization step. I have some slides in the end. If I have enough time, I will explain in details what I did for these two steps. But for now, it's just enough to make sure that these two steps are strongly dependent on the choice of the equations of a state. And whereas in the literature, all of those equations of a state, they had analytical solution, I went for those advanced equations of a state. And that needed a particular treatment, which I did in my thesis, and I can explain it to you later. The second model, the Kapila model, it has 5 equations. And as you can see, there is only one pressure. So why did I go for this model? The first reason was that, when you want to add all those tables, it has some computational costs. And especially for the relaxation and reinitialization step, it has some complexity. It needs some iterative algorithms in order to make sure that the pressures of the two components, they equalize through the relaxation step. But this model, it has the pressure, only single pressure. Although the sixth equation model, as you know better than me, because I know that you kind of developed similar models, the good thing with the Sorel model, with the sixth equation model, it has the volume fraction positivity at all the time, and also the speed of sound is monotonous. But I couldn't see any problem with that one either. So I tried to get some solution with this, and as you may know, the solution that this diffuse interface gives is kind of the same. I mean, it's, even in theory, they should converge to the same solution. So basically, both are diffuse interface method, both are compressible, fully compressible, and they converge to the same solution even numerically. But another reason to pick this model was that at the time, another colleague of mine, this great guy here, Armand Shams, he was using this model in order to develop some FSI fluid-solid interactions for the more or less similar cases that I was developing. So we were interested in collaboration and, to implement the FSI from his own PhD to also to couple them together with my complex thermodynamics. So we said that we can also consider this also in a more advanced solver, which is called AMRX. And the good thing with this, I mean, this is not a solver. The solver is developed by Armand, and added, the complex thermodynamics by me. What AMRX does is to provide a platform, basically, to solve the, the PDE, and it gives us the possibility of having the parallel processing, and of course, AMR in a block structure format, and it's very efficient. It works with C++. And also Fortran, it can be even parallel on GPU. So it's an amazing platform, but as opposed to many other open source solvers, it doesn't offer any solver by default. So it just gives you the possibility to develop your own solver with solving the equations that you want to solve. And yes, here's the result section. I would like to present the result sections separately for gas and liquid, so that we are investigating the gas and liquid thermal effects separately. And because I know that spherical collapse is more fundamental case, but non-spherical collapses are usually more, they have more applications. So I'm going to start with non-spherical collapse for each gas and liquid thermal effects separately. So this is the first test case that we have. We have this pressure pulse from the top boundary that I showed in the first slide, that we can use the bubble collapse for lithotripsy in order to break the kidney stone, and we all like to have some applications out of the PhD. So that's why I was really interested in this simulation, and I kept continuing this simulation till the end of my PhD anyway. So we have this lithotripter here on the top, and this is an axisymmetric problem. So we have this axis of symmetry here. We have the bubble here. This is just the initial setup, and we have this initial standoff distance here, the distance between the rigid wall to the center of the bubble. And here you can see the boundary conditions. And here we have also all the parameters that I used in order to do these simulations. And this is a pressure pulse, specifically from a real ultrasound device, a lithotripter, with removing, of course, a tensile part in order to not to have a big problem with the negative pressures anyway. So in order to investigate the real gas effects, I use all the equations of a state that I explained to you, and I just want to highlight the difference that these complex equations of a state, they make compared to the ideal gas. And for water, I use Stiffened gas for now, because the focus here, I'm going chronologically. So the focus here is only on the gas. For the Stiffened gas, we will see the results in the next section. So here is, I did the simulation again in 2D axisymmetric, but here is the 3D simulation the 3D representation of the simulation. So the bubble collapses non-spherically as expected, where we have this rigid wall on the bottom. And here's what we see in terms of the bubble dynamics. So I took this case from this reference of Eric Johnson, and we can see that the bubble dynamics is in a very great, excellent agreement with Johnson result. And the finding here is that the bubble dynamics is not affected by the equations of a state that we use for gas. So regardless of the gas equation of a state, you can see the exact same bubble dynamics that we can see for ideal gas. And here you can see just a 2D animation of how the interface is evolving during the time. And as we all love, this is the grid convergence for this case. So we can see that if we have like 150 grid inside the bubble initially, that's enough. This is with no AMR, of course, but this is another animation for the same simulation that we can see the bubble temperature on the left, and on the right we can see the numerical Eulerian, which can show just the shock emitted after the collapse of the bubble. So on the bottom we can also see the pressure of the wall, and yes, so we can see at the moment right during the moment of the collapse, we can see the highest temperature ever, which is about 5,000 kelvins. And this simulation is done with the real equation of a state of RKPR. And here are some snapshots. So again, we can see here that the bubble, only for very short time scale, it reaches the highest value of about 5,000 kelvins. And in the next slide, I'm going to show you how it can change if we use ideal gas, that is to ignore the intermolecular forces and also to ignore the variation of a specific heat with temperature. So here is the difference between the predictions of the bubble temperature with ideal gas equation of a state, the blue one, and with RKPR, which is again the best choice here, because in terms of the range, it has a very good range of applicability, especially at the higher pressures, up to I think almost or the order of gigapascal. Sorry. So here's what we can see is our prediction is almost 46%. And we are interested in also seeing the impact of the initial standoff distance. So remember that the initial standoff distance was the difference, was the distance between the rigid wall to the center of the bubble. So here we can see that as we set the bubble closer initially to the wall, the temperature of the bubble, during the collapse, it becomes lower because of non-sphericity impacts during the collapse, which makes sense. But if you, for example, have the initial standoff distance 2 times the initial radius or 3 times, we can see there is not a big difference because this is far enough for having more or less spherical collapse. And now moving to the spherical collapse, which, as I said, is a bit less interesting because in reality, we usually don't have any kind of spherical collapse, but it's still a nice representation of the development of the work. So I ran this case for 3 different pressure ratios. So everything is the same, as you can see, but the initial pressure ratio is different. So if we have, for the highest pressure ratio, 373, and for the lowest one, we have the pressure ratio of 7. This is just a schematic of the setup, the boundary condition. We all know how it works, and we would like to now see how the equations of a state plays a role. But before that, this is again the grid convergence for the same simulation of the lower case. But let's see how it affects the gas equations of a state on the temperature of the bubble during the spherical collapse. So it's observed here that with the ideal gas equation of a state, again, it's due to ignoring the intermolecular forces. So it's, intermolecular forces, they make a kind of endothermic processes, and that absorbs energy. So it's kind of expected to see that the temperature prediction by the advanced equations of a state, they are lower, and this is more, closer to the reality. And even that can be lower if we take chemical reactions or the other complex phenomena into account. And by the way, I just did the non-dimensionalization with the initial radius and the Rayleigh collapse, just to be consistent with the references. And quantitatively, we can see in the table that the ideal gas predicts the maximum collapse of temperature above 9,000, whereas it happens only 6,300 if we consider the RKPR equation of a state. And that's where the first journal publication of my PhD comes up, which we can see later if I have any questions about whatever I presented so far. And now let's move to the thermal effects for the liquid. So we have again the same case of having the lithotripter pulse on the top. This pressure pulse is traveling to the downside, and this time we have also the AMR grid here. It's basically the same case, and for the air, because we concluded that for the gas it's better to use RKPR in order to enjoy even the higher range of validity. For the air, I'm just going to use the RKPR, and for water, I'm going to use the MNASG. And let's see how liquid equation of a state plays a role. This is just a schematic of the simulation, just to see how the AMR works. The bubble collapses obviously non-spherically, and the microjet creates the force there. But this one probably is more relevant to my job. So again, on the right, you can see the bubble, and on the left is just the liquid temperature. So we can, what we are interested is to see how the liquid temperature is evolving in this region, and as I said, along the wall axis, because the liquid temperature along the wall axis, it can give us like a clue for thermal damage, which has more application if we model the FSI, which I will show some slides later, to find some mechanisms responsible for the thermal damage. We need to have an idea about how the temperature of the liquid is evolving there. And this is again the bubble dynamics over time. So as we see again, this is a good agreement with the reference, and also with the paper, and the paper was obviously about with the Stiffened gas for the liquid. As I said, back then I didn't use any more advanced equations of state for liquid. So we can see that the dynamics of the bubble is not going to be affected by the choice of the equation of state, even for liquid. And we make this conclusion even for the gas phase. So here is also the schematic of the collapse procedure. And again, we can see that right after the collapse, there is a high temperature region above the bubble. And again, we are interested in monitoring this temperature here, which I'm going to present some plots here. So this is the variation of the liquid temperature along the wall axis at different times. So we can see that at some point it can get to 325, which is essentially 25 degrees of Kelvin elevation of temperature compared to the initial setup that we had, which again, it can be kind of representation of the thermal damage. And this is the impact of the standoff distance on this temperature, the maximum of the temperature. So we can see here, if we have the standoff distance lower, then the temperature of the wall, the liquid temperature along the wall will become higher because, So this one is again a bit more difficult to understand, but the horizontal axis is showing the time, and on the vertical axis we are seeing the wall axis temperature, and this is how it is evolving during the time. So We can see here the maximum is almost around the collapse, and it's happening very close to the center of the bubble, near the axis of the symmetry. And we're going now to see some thermal effects in a spherical bubble collapse for the liquid. So I did the same simulations for the liquid side too. So we are changing the liquid equation of a state. We have the Stiffened gas, we have MnASG, we have also the experimental equation of a state, which is also again like a benchmark for us to compare the results. So we can see that right after the collapse, there is a temperature front caused by the spurious kind of temperature front, or fake temperature front by the Stiffened gas. And the magnitude of this overestimation is not negligible. And that was the motivation where we started applying some other equations of a state. And we can see that with MnASG, we don't observe such a fake temperature. But the problem again with this one was that this is, as you can see, this is a low pressure ratio case, because this experimental equation of a state, if you go to higher pressure ratio, it fails. And that's where the MnASG, which I think it was developed, or I think NASG was developed just a few years ago, and MnASG I think it's for maybe 2-3 years ago, which they can be very good options. And I should also point out that there's another extension version of the NASG, which can also add some more effects in lower scale, like intermolecular scale, but with much more details. But I tried that one as well, but it was not really working for high pressure ratio cases, and maybe that's why we don't see many citations for the extended version of the NASG, but who knows about the future. This is the temperature front that I was talking about when using the Stiffened gas. So on the right side we can see the Stiffened gas, and on the left we can see the simulation with MnASG. And of course it's observed here that the time scale for this temperature front is very small, but still it's something there that we cannot ignore. And we don't know, for example, in some applications we have multiple collapses, and also we have sometimes, collapses of the cluster of the bubble. So where this temperature, the fake temperature, they can play a role in some applications. And to go back again to what I said about the two numerical methods, the 6 equation and the 5 equations, I just want to show you here that they both reached the same solution again. This is theoretically and numerically proved in other studies too, that Kapila model, the 5 equation model, is less stable. So sometimes there are some numerical tricks that needs to be done for initialization, for example. 6 equation model is more stable, but it has some more difficulties in terms of adding the relaxation and reinitialization stuff, because this is mechanically disequilibrium. So we would like to have this equilibrium through the relaxation step, but the result is the same. If Kapila is managed to do that, then the result is the same, which, to the best of my experience, Kapila is working really well. But both of them are advanced diffuse interface method, and based on, again, this is kind of surprise for me because it was the best gift I could get from ultrasonic summoning chemistry. It was a very beautiful email after submitting, I think it took less than 30 days to get this one accepted. And following the discussion that I had before about the collaboration with Armand, we went through applying the complex thermodynamics to the FSI solver that he has. So his solver is also on AMRX, so implementation was really easy. We have the hydrogel here instead of rigid wall. So this is the exact same case that I was presenting. Again, we have the ultrasound pressure pulse from the top boundary, but instead of the rigid wall, we have hydrogel here. And to the best of our knowledge, this is the first time that that thermal effects is going to be studied in this detail with having the FSI. And this is the animation of the simulation that we It's very new, so it's very recent. We got it quite recently, and we can see how the temperature is evolving on the top, and the maximum principal stress on the bottom. And there's another one animation that we can see also the pressure as well. So there are kind of different mechanisms here for the thermal damage on the solid tissue. One is the pressure pulse that is, coming from the top boundary, and another one is caused by the shock emitted after the collapse. And another one, the last one, is when the bubble is migrating after the collapse towards the wall. So all three mechanisms, they can increase the wall temperature, and we wanted to make an approximation how this temperature, the magnitude of this temperature, how much it will be, because it can give us a clue during the ultrasound lithotripsy, how much the temperature elevation will be. And this is also very applicable, but again, we should not forget about the assumptions that we have here. We don't have, for example, the viscosity or conductivity, for example. We don't have the conductivity here, but this is just very good, simple first step towards more complicated things that it can be continued by probably other researchers in the future. So I think I have like 10 more minutes, but because we have 10 more minutes, I'm gonna show you some more results. This is the literature review that I did in almost the beginning of my PhD about the existing studies where the temperature of the gas inside the bubble was studied using non-ideal equations of state like van der Waals, which considers the intermolecular forces, but not as good as Peng-Robinson or the variation of Peng-Robinson, because I think the repulsive and attractive terms for van der Waals are not that great. But regardless, why I didn't use these, here I added that this is a 0D model. Why didn't I use a 0D model? Because they're able, at least originally, 0D models like Rayleigh-Plesset or Keller-Mixis or Gilmore, they are valid only for spherical collapse because they are just tracking a point. There is no dimension there. So whereas we are interested more in like applicable, like with practical cases like what I was showing to you. And also these variation of 0D models are usually weakly compressible. Rayleigh-Plesset is incompressible, but the variation might include some compressibility. And another thing was that with these 0D model, due to their nature, we have, we consider spatial uniformity of the variables inside the bubble. So that's why I didn't use them. And the number of studies using the real equations of state in multidimensional solvers are very limited. I could find only this one where argon was simulated for a non-spherical collapse. It goes to 2016, but I couldn't find any other relevant simulation or study. And this is also, I was also interested in seeing how much the temperature is predicted in general. I think overall in the area of bubble collapses, the interest has been more on other things than thermodynamics. And that's why the PhD topic of mine, it was, it has some room to improve. And I think we have still some time. So I just want to show the numerical novelty of my thesis for the 6-equation model. So as I said, in the 6-equation model, we have two different pressures initially, but we have this system of equations that they need to be solved at the same time, right? And if we have the pair of a Stiffened gas and ideal gas, we don't have any problem. The problem happens if we have more complicated parametric equations of a state, or if we want to apply more complex equations of a state in tabulated format. And this is where I said that it needs to be solved iteratively. And this is a solution if we have equations of state based on the Stiffened gas. So it's pretty easy to implement that in that cases. And This is again a shock tube test, which was the benchmark. Again, I ignored it in the first presentation because I thought maybe it's going to take a longer time, but this is just for the sake of validation. I run this very famous shock tube and I validated the code with all the equations of state that I used. And another test case was the cavitation test, where we could see again the RKPR is valid even for the shock tube at high pressures and cavitation test. And this is another one with a lower pressure ratio case, which we can see that if the pressure ratio is not that high, then the difference between the prediction of the ideal gas and the real gas is not that high. So it's, the over prediction of those equations of state, it always depend on the pressure ratio. And this is also the spatial temporal figure for showing how the gas temperature or the air temperature is varying over time. And as you could see, the additional physics or thermal mechanism for the gas is not going to change anything before the collapse moment. So this region is the same as this region, but right after that, right during the collapse, we can see that here the temperature, the maximum is 10,000, whereas the other one is 6,000. And the next slide is just to show again the same basically concept, that the maximum temperature happens only during the collapse. So regardless, because this is almost adiabatic process here, so regardless of the equation of state, we get the same results here. But for predicting this, the highest value during the collapse of the air, then we need to use advanced equations of state. And I think I have 5 minutes, and maybe it's enough. I just want to make some conclusions. So the novelty of my work was to implement the generalized algorithm in order to include any kind of equation of state with the same solver. So regardless of the thermodynamic model, whatever you have, you can just put it in the table, and then to implement it and do the simulation, and also to obtain some insights about the liquid and gas thermal effects. And there are some findings that I explain all of them to you, but just as a review, we concluded that the ideal gas and the Stiffened gas are not the best choice when it comes to thermal effects, and it's better to go for more advanced equations of state. And the problem here is that, of course, the experimental data are always preferred, but the problem is that the range is very limited, and then we have only cubic equations of state. And the MNASG, which is a more advanced model for liquid. Another finding was that the real gas model, it predicts a space average temperature reduction in bubble interior up to 41%. So speaking of the number is 41%, and a maximum of 50% locally. So of course in local, the local difference can be smaller compared to the average, because this is even locally limited to the center of the bubble. And for the conclusion, I would like to also mention that there are some improvements possible. Of course, like any other studies, we have some possibility of expanding this study. So one of the suggestions that I would think would be a good idea is to add the vapor inside, because vapors, they behave differently from air, and usually we have vapor in the practical cases. We have vapor as well, because the bubble is usually a mix of air and vapor. So that can be a very good idea to continue, and also to add the conductivity and chemical reactions. Of course, it depends on the situation, the case that when they can play a role. Sometimes, if your temperature doesn't go to crazy value, then modeling chemical reactions has no importance. Another idea is to simulate 3D cases to model clusters of bubble, or some more advanced practical cases that we can have. 43, okay. And there are, as I said, these numerical solvers that I developed, they are not limited only to bubble collapse, so we can always use them for any multi-phase flow where thermodynamics plays a role. So from combustion to anything, especially where the thermodynamics is extreme. And as a final word, This is the first picture is IICR in Khania, where I met Stefan for the first time there, and we had some very fun time. I remember the dancing as well and having great wine there. And this is for the last one that we missed Stefan, unfortunately, because he was somewhere else. He was busy with another conference, I think. But still, we have Dieter and Manolis there. And I remember Chagi, but I don't have any picture, unfortunately. Sorry about that. And this is the team at City University. Majority of them I don't think you know, but Manolis is there and Andreas is there. I should also thank Andreas as well as Phoebus. They contributed a lot, especially Phoebus to my PhD. He's very knowledgeable about thermodynamics, and I really need to appreciate his effort. Now I would like to also thank Gail and Jan from ICR, and they supported me a lot during the time that I really needed support. I would like to thank them. And finally, I would like to thank European Union for sponsoring my PhD through the Marie Curie Fellowship, and also thank all my colleagues, including Arman and all the other colleagues at City, and for the very good time that I had here. Unfortunately, it was due to the pandemic. I was here only for 4 months, which was really sad, but still, I have the best memories here from D'Alembert. And of course, I would like to thank my family. I know that they are following my presentation from YouTube, so wherever you are, I love you, and you mean a lot to me, and I have everything from you. And that's the end of my story. Official education is going to end today. I mean, hopefully after the signature, I hope that I will get it, but that's, the beginning I studied, I started going to school at 6, and after 29 years, it's a weird feeling to say goodbye to official education. Unfortunately, I think there's no possible further extension for the PhD or that sort of thing. Still, I'm interested in research, and I would like to continue. Well, yes, why not? I mean, I hope. Thank you so much. Thank you so much.
Okay, thank you for your presentation. So we'll move to the questions, and we will start with the reviewers. So we'll start with Dieter. Do you want to start the questions?